Okay, so good morning, guys. So we will get started. Now we will today move on to a new topic. Okay, no, get to the chat first. Are you guys there? Okay. Okay. Very good. Sorry, I was not able to take how many sessions? 2 sessions. I was down with Omicron, so I'm back. Okay. So 2 sessions we missed thanks to Omicron. So don't blame it on me. Blame it on Omicron. Okay, we get started today. So today what we're going to talk about is an interesting area which I think it's time to start, which is pointers. P-O-I-N-T-R-S, pointers. I would want to finish pointers first, then go to functions and then go to other areas. So let's start with pointers first. Now, have you heard of pointers? Anyone? Yeah, I'm taking good care of my health. Okay. Anybody heard of pointers? Okay, some of you have. Okay, good. Okay. Yeah, it's an address of a kind. So we'll work with pointers. The best way is to learn it through example. As we start writing code, you'll understand how to work with pointers. So let's go back a little and understand what happens when you say int x. When you say int x, what really happens? I think I described it to you, for some of you at least. A memory gets created. The name of that memory is x, and what is the size of this memory? It is, on most systems, it is 32 bits or 4 bytes. That is the size of the int. So an int has 4 bytes on 32 bits, but I think you should know that this may change. The size of an int may change from system to system. Now there is an operator which enables us to say size of anything. We can find the size of int, size of anything. So when you say int x, so size of int, or you can even say size of x, okay, that will be equal to 4 in our case, most of the time. Now it may be true or it may not be true, because C doesn't say that the size of an int should always be 4 bytes. Sometimes it may be 4 bytes, sometimes it may even be 8 bytes, sometimes it may be 2 bytes. Unlike languages like Java, where the size of an int is always 4 bytes, no matter on what machine you are running. In C, the size of an int depends on the machine on which you are executing the code. So on the machine on which you are executing the code, that decides what should be the size of x, okay, or size of int. As I said, it may be 4 bytes, 2 bytes and all. And the same argument applies whether you are discussing short, long, float or double. Okay, any of these data types depends on the machine on which you are running, whether it's an Intel processor, whether it's a Spark processor, whether it's a reduced instruction set computer. Depending on the kind of machine you are working with, the size of short, long, float and int may vary. So size may vary. Okay, anyway, we are not talking so much about size, but I think it's important and pertinent to know. So when int x is done, a memory location is created somewhere in memory, and the name of the memory location is x. So this somewhere is called the address of the location. that is at some address we have X sitting at that. Now C and C++ enable you to understand or see what is the address. Other languages like Java or Python, you cannot get the address of a variable. Only in C or C++ you can get the address of a variable. Anyway, is it a physical address? Well, not really. It is a virtual address, but we'll talk about virtual to physical mapping and all that later. When you do more of operating systems, then we can talk more about what is a virtual address, what is a physical address, all of that can come later. But C and C++ are perhaps the few languages which enable you to see or get the address of a variable. Other languages will not permit you to get the address of a variable because they feel there is no need and it may end up confusing you rather than helping you. But the C++ was designed to give you an address. Okay. Now, how do I get an address? So let's talk about that a bit. So I will say int x. So I say x is created somewhere in memory. As I said before, x is created somewhere in memory. Now, can I get the address of x? Yes, you can. One way of doing it is you can simply say printf. You can use %d or %x. Sometimes we use %x, x or 0x, %x. To get the hexadecimal, generally addresses are mentioned in hexadecimal. We can say ampersand of x. Okay. So this way we can get the address of a variable. So just say ampersand of x and we say in hexadecimal. You can also use decimal here. You can also use decimal, but generally in all our computer science, whenever we are discussing addresses, we get addresses in hexadecimal notation. So if you want the address to come in hexadecimal notation, you say %x and you say ampersand of x. This is the way you can get the address of a variable. Okay. Then there is, let's get this out of the way. Let's write this in our code so that you are familiar with it. Let's open a practice question and see whether we can do it.
Practice lab 12.
Okay, it is, please open practice lab 12 so that you can practice with us. Okay. So just watch the code. We'll write a small piece of code to work with addresses and pointers today. No, just say int x. Int x and then say printf %x. You're not ready, yeah? Forget చేశాను ఫేస్ ఎట్లా ఉంది అని %x పెట్టండి %x ampersand of x. So let's run this because we have said int main, we are doing that. Okay. Yeah. So you open it up. This is a hexadecimal notation of an address. Yeah. So you can see this. You'll get some other address. Doesn't matter. Every machine may produce a different address. Every time you execute, it may produce a different address. So this is the hexadecimal address. As you can see, it's hexadecimal. It has numbers and letters up to F. So that makes it hexadecimal, correct? I think that should be adequate to understand that it's a hexadecimal address. You can also print it in decimal form. If you're comfortable, we can print the address in decimal form. So you say %d and run it. You got the address in decimal form. Now you get a negative number. You see, because we are printing it as a signed number. Later we'll talk about why we get a negative address. It's actually not a negative address, it's a positive address. Only thing is we have to say it should be an unsigned int. The address should be unsigned. Doesn't matter. That's why we print it in hexadecimal manner. Okay, let's go back to hexadecimal only. Okay, so we generally use hexadecimal notation. Okay, now let's talk about pointers. Okay, so how do I create a pointer and what is a pointer? Don't know.
One of the student has a question.
Question. Okay. Somebody has a question. It's important. We'll talk. Is the address in my computer? No, it's in the tesslator only. Everything is in the tesslator. Why is it showing a warning when I use %x? No, I am not getting a warning.
We are getting. We
got a warning?
Yeah.
Okay, why? I don't know. Why do we get a warning? Let's see what is the warning. It shouldn't give a warning.
It's a hexadecimal warning.
For hexadecimal, we are getting a warning. Right? Okay, let's see what warning we get. An argument of type. That is that unsigned int. Yeah, you remember when we were printing decimal, we were getting a number. So we should get an unsigned int. Anyway, don't worry right now about it. We are not talking about signed, unsigned. Don't worry about it. Think it is an address. Okay. Now, same time I am getting two addresses. How can I have? No, you shouldn't get two addresses. You should get %e, x and %d. They are the same address. So one is in decimal format, one is in the hexadecimal format. I don't know why you're getting confused. Yeah, no. Unsigned int is also giving a warning. No, that is I have to cast that variable into an unsigned int. The $x, I have to cast it. If you want that warning to disappear, here it is. We can do this. Ampersand of. Line 6. Ampersand of unsigned int. The x తీసేసి అట్లా కాదు కాస్టింగ్ లో పెట్టండి no baba unsigned int then yaar దాని తర్వాత అన్సైన్ ఇంట్ తర్వాత ఓకే ఎక్స్ ampersand ठीक है ampersand of unsigned convert x into unsigned int and then let's see now try to compile no we still get
the total ampersand value has to be
this has to be
no
unsigned int of ampersand x.
Unsigned int of
ampersand x.
Ampersand x.
Keep that in bracket. Ampersand x. That's all.
Let's see. No, see where the warning is coming.
Still it is coming.
No, it's still coming. Cast from pointer.
Integer of different size.
No, there is some. No, it shouldn't come. We have converted the address into an unsigned int. No, we have to check. Okay, don't bother so much about it. We'll check. Let's go back to %x, ampersand x. Remove that unsigned int. Okay, we'll worry about it later. Don't worry right now. Just think of it as an address and we'll proceed. Okay. So, okay. Now let's come to the main issue. Yeah, we'll figure out why it is giving a warning there. But it's important to know why it is giving a warning. Now, how do I create a pointer? So I say int star p. This is how you create a pointer. Now let's pause a bit and understand what's happening on this line. Now, when you put star before a variable during its declaration, now please understand, I'm repeating, when you put star before a variable in its declaration, that is when the variable is getting created. Now what is p? P is not an integer. P is an address of an integer. P can hold an address of an integer, or P is a pointer to an integer. We can say P is an address or P is a pointer to an integer. We can either say it both ways, it means the same. So now let's see what happens in memory. So when I said X, this variable got created. When I say P, also a memory gets allocated for P. Now what should this hold? This should hold an integer. What should this hold by its very declaration? This should hold an address of an integer. Please understand the difference. X, when you say int X, X holds an integer. When I say int star P, what is P doing? I am creating a variable P. P also takes a certain amount of memory. How much memory will it take? Big enough to hold an address. How big is an address? Generally on most systems, an address is also 4 bytes. Most systems, addresses are 4 bytes. But as I said again, there is no hard and fast rule how big the address should be. In many of our cases, an address is also 4 bytes. But you should understand, P is capable of holding an address. Why did that happen? Because look at the way I declared P. I said int star P. That means P is a pointer or P is an address. Address of what? Address of an integer. So P should hold the address of an integer. Now, right now what is P holding? Junk. What is X holding? Junk. So I can remedy that here by saying X is equal to 5. When I say X is equal to 5, what happens? A value 5 sits in this memory location X. When I say int star P, P holds the ability to contain an address. So P is going to be an address. But right now P is garbage because I have not made it point to anywhere. But now look at this line. P is equal to ampersand of X. Now this is the super important line. P is equal to ampersand of X. Now what does it mean? We just saw ampersand of X contains an address of X. What are we making P equal to? The address of X. So what P will now contain is the address of that variable. So P will contain this address. Suppose let's pretend this address is in memory at location 5000. That is where this is. I'm just taking this as a notional value. So what will P contain now? P will contain the address of X, not the value of X. It will contain address of X. So P will contain 5000 in this example. So P is going to hold the address of X because of this line. By this line, what are we saying? P is going to hold an address of an integer. By this, we are simply saying P is going to hold an address of an integer. By saying P is equal to ampersand of X, we are saying P will now contain the address of this variable, which we are notionally saying as an example is 5000. So P will contain 5000. Now, let's create another variable just to drive home that example. Int m. You can create it above also. So int m, I have created another variable which is of type integer. Now I will say m is equal to star of p. Now you have to understand this. M is created somewhere, okay. This is m. When you do this line, m gets created like this. M is created somewhere in memory. When I do this line, m is equal to star of p. Now this is not a creation of p. This is called a dereferencing of p. It's called dereferencing. Dereferencing of p. This is called dereferencing of p, which means p contains an address of something. Go to that address, get the value sitting at that address and put it in m. So when you say m is equal to star p, this p has to be an address. So go to that address, whatever that address is, go to that address, retrieve the value sitting at that address, which in this case happens to be 5, and assign it to m. So now m contains the value 5. Okay. So we are going to do this, and it will take a little while for you to get used to it, but it is very easy. It's not difficult, and we can quickly get used to it. So I think this should make you understand. I am going through the steps again. X, when you create int x is created with some memory somewhere. When you say x is equal to 5, 5 goes and sits in that location. Okay. When I say int star p, p is created, but p at this point will have junk. Only restriction is that p is going to be an address of an integer. That is, p is going to contain the address of an integer. This is what we actually do. P is equal to ampersand of x. We bring the address of x and put it in p. So think of it like this. Get the address of x and put it in p. P can contain only addresses because it's declared like a pointer. A pointer is nothing but like an address. So now I declared m, I can declare it above also. So I said m is equal to star of p. Now what happened? I went to the location p, which is 5000, or I went to the contents of p, 5000, I took them, I treated this as an address, and then went to the location 5000, got the value which is sitting at that location and assigned it to m. So all that happened. Okay. So now let's do it in our program and see what we get, and then we will do a little more work. Okay. So let's do this. We declared m. Now we can remove that printf. So we will say int star p. Okay. Then we will say p is equal to address of x. Okay. We will say x is equal to 5. So in that location 5, we are putting location x, we are putting 5, and then we are saying m is equal to star of p, dereferencing of p. Okay. So now we'll say printf %d m. No bubble. Bracket. Yeah. So we have got m. So let's see what we get. Yeah. So as expected, we get m equal to 5. Okay. We got the answer as 5. Okay. Now that was expected. Okay. Now, go back to the. So again, at the cost of repeating a bit, this creates two memory location X and M. So this is a memory location X, this is a memory location M. I'm just walking through it. This creates a memory location P. This is going to hold an integer. This is also going to hold an integer because of this declaration. This is P. This is going to hold an address of an integer. Right now it is junk. This is also junk. This is also junk. Now what does this line do? Line 8 do? X is equal to 5. This puts 5 here. M is equal to star of P. Now what does, sorry, I forgot this line. P is equal to address of X. So wherever X is in memory, let's say it is 5000. Okay. Let's say this is, okay, let me write 5000 clearly. This is 5000. So it is 5000. And let's say M is at 6000. That doesn't bother us right now. M. So M is equal to star of P. No, before that, P is equal to address of X. So P contains the address of X. So P will contain 5000. Then X is equal to 5. We already put 5 there. M is equal to star of P. Go from 5000 location, go to the address 5000. Treat this as an address and go to the address 5000. Get the value sitting there and put it in M. So now I have 5. Okay. Okay. So now, okay, let me ask a simple question. Okay. Suppose I say now P is equal to address of M. Okay. And I now say, okay, that's very easy. Look, let me create another pointer. Okay, let me create another pointer. Let's call it
P1.
P1. Okay, so no, let's call this P1. P1 and P1. So we'll create another pointer. So this is P1. We'll create another pointer P2. How do we create it as a pointer? I'll say int star P2. Okay. And I'll say P2 is equal to address of M. Okay. And then I'll say, so after this, let's say I am doing int star P2. P2 is equal to address of M. And I'll say now star of M, okay, is equal to star of P2. I can't say. Okay. Let's say star of P2 is equal to star of P1 plus 3. Okay. Now this is a good question for you. What I am doing is, as a continuation of this program, I am creating another pointer int star P2. I am going to say P2 is equal to address M. This I can create at the top also. I am going to say P2 is equal to address of M, and then I am going to say star P2 is equal to star P1 plus 3, and then I am going to say printf percentage %d and M. Okay. Let me write it for you, and then we will see whether you can predict the correct answer without running it. So, okay, we'll rub this off. Yeah, okay, some of you are getting it okay. Go to the code. Now we'll declare one more pointer. Let's call this P1. So wherever P is there, let's change it to P1. And let's create another pointer int star p2, and yeah, let's say p2 is equal to address of m, and then let's say star of p2 is equal to star of p1 plus 3, and then we are saying printf percentage dm, no? Okay. No. So let's first analyze it. Let's trace it, and then we will execute it and see whether we are getting the right answer. So let's trace it. Let's trace it first. I'm tracing it line by line. So what does line 5 do? It creates two memory locations, X and M. As we said, at memory location, let's say 5000, at memory location 6000. Two memory locations are created, X and M. We are notionally saying or assuming that the address of X is 5000 and the address of M in memory is 6000. So now we have created two pointer variables, P1 and P2. So this is P1, this is P2. We have created two pointer variables, P1 and P2. Now we are saying P1 is equal to address of X. So at this stage, what will P1 contain? Address of X, which we are notionally saying is 5000. X is equal to 5. So X is equal to 5. M is equal to star of P1. So go to P1, do a star on it, that is do a dereferencing on it, that is take the address sitting at P1, go to that address, get the value which is there and assign it to M. So at this stage M will become 5 at line 10, yeah. So at line 10 M will become 5. Okay. Then what am I doing? P2 is equal to address of M. So P2 will now contain 6000. This is 5 please. Then star of P2. Who is star of P2? This one. This location is the star of P2. So star of P2, which is this value, that location of M, star of P2 is equal to star of P1. Star of P1 is this value plus 3. So this will contain 8. So this will contain 8. So when I print this answer, I should get 8. Okay. So let's check it out whether we get 8 or not. Yeah. So as you can see, if you are seeing my screen clearly, you will get the answer 8. I got 8 because that's what I did. So let's play with it a little bit more. Okay. So now let's do one more thing. Let's put 2 more lines here just to add a little more variety. After this line, let's add 2 more lines. We will say star of P1 is equal to now star of P2 plus 10. Okay. And then we will say star of P2 is equal to star of P1 plus let's say 5. Okay. And then I will print M first, or rather I'll print X first, and after that I'll print M. So can you now guess what will be the value of X and what will be the value of M? I'm adding 2 lines here. Star of P1 is equal to star of P2 plus 10 and star of P2 is equal to star of P1 plus 5. So remember what was the situation before we came here? We had X which was having a value 5. I am saying up to this point till here. What was the situation? X was 5 and M was 8, if you remember, and P1 was containing the address of X, which we said is notionally 5000, and P2 was containing the address of M, which we said is notionally 6000. Okay. So that being the case, we have P1 at 5000, this is P2, 6000, and now what we are trying to do is star of P1, we'll come to that in a moment. Let's first see what happens here. Star of P2, that is, it will take 6000, go to the location 6000 where it will find M, retrieve the value, so this will be 8 plus 10 will be 18. So where will 18 go? Star of P1. Star of P1 is this location. When you go to P1, if you do star of P1, you get this location. So here instead of 5 it will be 18. This value will be 18. Then after that, so at the end of this statement, X will be 18. Now what we'll do? Star of P2, that is, we go to this location. Star of P2 is equal to star of P1 plus 5. So this will become 23. 18 plus 5 is 23. I'll get 23. So I'll get displayed 23. If I display now, after I do these lines, these two, I should get 18 and 23, right? Let's see whether we get that. If you're getting it that way, our logic is correct. Our understanding is correct, rather. Okay. So we'll put those two lines after that. We'll say star of P1 is equal to star of P2 plus 10 and star of P2 is equal to star of P1 plus 5. And then we'll print X first. No, value of X. Okay, value of X is equal to X. And value of M. Good. Yeah. So now see what we are getting. Value of X is equal to 18 and value of M is equal to 23. Okay, as we expect. So this is what we should be able to get. Okay. Okay. Now, do you understand what is happening? Okay. Okay. So now, since we know some basics about pointers, how to reference it, how to dereferencing. Now, let's understand what is the meaning of referencing and dereferencing. So when I say there is int x, okay, and int star p1, when I say this is called declaration of the pointer. Here only the pointer memory is allocated, but the pointer p1 doesn't point anywhere. Now p1 is equal to ampersand of x. This is called giving a reference of x to p1 or giving the reference of x to p1. reference means address, or it can also be said giving the address of X. Reference is address of X to P1. Okay. So this is, we are giving the address of X or reference of X to P1. So this is why this is called a referencing operation. This is a referencing operation. When I say print F, or I declare any other M, and I say M is equal to star of P1. Here what I am doing? Here I am going to the location given by P1, that is given, I am going to the address in P1, going to that address, and first I am getting the address, going to that address, getting the value at that address, and putting that in M. So this is called converting a reference into a value. This is converting a value into a reference. That is what it is called, or getting an address of a variable. This is called going from address to value. Here it is value to address. Here it is address to value. So this is called a dereferencing operation. So when I say dereferencing, that means I am getting the value pointed to by that pointer. So this is called dereferencing. This is called referencing. Okay, this is just some nomenclature which is used often in computer science. You should be familiar with it. Okay, so we have understood what is a reference, what is dereference. Okay, now okay, let's do a little bit more, and we will talk a little bit more. Okay. Okay. Since we are here, now I have said int star p. Okay. Now I will introduce a double pointer, int star star p. Okay. So look at the way it works. Okay, how I use this. Sorry, P1. This is P2. Sorry. This is a single pointer. This is a double pointer. Double pointer means pointer to a pointer. Now I say P1 is equal to address of X. Okay, let's put X equal to 5. P1 is equal to address of X. So if X is created at location 5000, what will P1 contain at this stage? This is P1. It will contain 5000. Correct? Because P1 contains the address of X. Okay. Now P2 contains address of P1. Remember, P1 is also a location in memory which holds the address of X. And what is P2? It is an address of an integer. 2 times. It's called double indirection. Double indirection. Or you simply call it double pointer. P2 contains the address of P1. P1 is also in some memory, somewhere in memory. Let's say 12,000. So P2 will contain 12,000. What is 12,000? Address of P1. What is P1 containing? Address of X. And what is X containing? The location 5, the value 5. And where is X sitting? At location 5000. Yeah. Where is P1? At location 12,000. What does P1 contain? Address of X, which is this 5000. What does P2 contain? Address of P1, which is this 12,000. Now, if I say M is equal to star P2 plus 7, what will this do? Now see what is happening. I am going to P2. I am getting the first star of P2 will take me to P1. the second star, so think like this, star of P2. Star of P2 is 5000. Star of P2 is 5000. P2, because P2 is 12,000, it's an address. You go to that address, what is the value sitting there? 5000. So star of P2 is 5000. Star of that, dereferencing of that is this location. Go to that location, whatever is the value there, add 7 to that value. Okay. So I will get here, in place of 5, I will get 12. So this is called double dereferencing. Double dereferencing. The best way to think of it is, this is star of P2. Star of P2 itself is an address, which is P1, which is the address of X. When you do star of that, you go to that location X, and there you are doing plus 7, so you get 12. So it is like a double indirection, and double dereferencing is required. And how do you create it? You create it this way. Okay, so let's create it that way and check. We'll continue in the same example. No. This will.
We'll start another one.
We want to start another practice lab. Okay. That way this will be preserved. Okay. So we'll start a fresh practice lab so that the double pointers are in different. So please work with practice lab 13 for double pointers. Practice lab 13, please. Remove everything. I know it. I think again you can keep. Int x, comma m. Okay. We have x and m. Then we are saying we are creating a single pointer P1. We are creating a double pointer P2. Now P2 is a double pointer, please. Now we are saying P1 is equal to P1 is equal to address of x, or first say x is equal to 5. Okay. We said x is equal to 5. P1 is equal to address of x. P2 is equal to address of P1. Yeah. Now we'll say star of no, m is equal to, sorry, the line we wrote was m is equal to star of P2 plus 7. Then we said printf percentage d of m. Okay. So let's see what we get. Yeah. Okay, good. Yeah, as expected, the value of m is 12. You know why we got that, right? M is equal to star of P2 plus 7. Okay. So that's how we got the double pointer to action. Yeah, brackets are not needed. No, not needed. Okay, so now let's draw some more story. No, let's go to the maybe. Okay, now let's do something more. Okay, so as usual we have x and m. So let's say this is x, okay, and let's say there is a value 5. M, let's say there is a value 7. Now what we are going to do is we are going to use P1 is equal to address of x, P2 is equal to address of m. Okay, we are creating these separately. P1 contains the address of x, P2 contains the address of m. Now P3 is a double pointer or a pointer to a pointer. I shouldn't say double pointer, I should say pointer to a pointer. So P3 is containing the address of P2. Okay, P3 contains the address of P2, and now I am going to say star of P1, okay, is equal to star star of P3 plus 10. I think you know what is going to. I don't know whether we need to do it. So here what's going to happen? This is just to revise. I have star of P3, star of P3 will be P3 is the address of P2. So star of P3 will give me P2. Star of P2 will bring me here. That is 7 plus 10 is equal to, and what is it assigned to? Star of P1. Star of P1 will bring me here. So at this stage the value of x will be 70. So the value of x will be assigned to 70. I think that is self-explanatory, and we will get answer as 70. Does everybody get that? Yeah. Now, is everybody understanding what we are doing? We are doing it 2-3 times so as to explain what is happening. Okay. Yeah. Okay. So that's good progress, and let's move on now, because you seem to be getting, some of you at least seem to be getting. Now there is no way to check whether all of you are getting or not, but at least some of you seem to be getting what needs to be got. Now we are going to play a little bit with arrays, okay, and pointers. So let me move ahead. Arrays and pointers. Now we are going to really have fun. Okay. Now I am going to create an array int arr 10. You know what this does? It creates an array of 10 numbers. It creates an array of 10 numbers, and that name is AR. Okay. Now, a lesser known truth is the name of the array. The name of the array is a pointer to the first element. The name of the array is a pointer to the first element. Okay. Please understand this. Name of the array is an address. Remember, that's why we don't have scanf, we don't do %ARR. So name, I mean, if you're taking an element, you say %ARR of I, but if it's a string or something, name of the array is the address of the first element. Please get this etched in your mind. So, name of the array is ARR. That is the address of the first element. This you should know. So, I can say now int star p. Okay. If I say int star p, and let's say this array is at a location 1000, that is the first integer is at 1000, the next integer is at 1004, the next integer after that is at 1008, and so on. So now if I say this p is an address, now p contains the address of an integer. Right now p contains junk, ARR is this, okay, int ARR 10. Now I write, okay, p is equal to ARR. This is valid. Okay. You can't say ARR is equal to p because ARR is fixed. It's a constant address. Okay, is the constant address of the first. That is, ARR can't change, but p is just a pointer. P is equal to ARR is fine. Now I will say star of p is equal to 15. Okay, and after this I print ARR of 0. I will get this value because p is equal to ARR. Now p also points to that first. Remember, the name of the array is the address of the first element, so p will also point here. And when I say star of p is equal to 15, it is going to put 15 in this location, right? So let's check this out. Let's do this and see whether it works. Okay, so he will, okay, he's starting another practice lab. Okay, so we are starting another practice lab for arrays, practice lab 14. So please shift to practice lab 14, and this is practice lab 14. We'll erase it, most of it rather. Int ARR of 10. Okay, and then let's say int star p. Okay. Then let's fill up the array with some values. Let's write a small loop for we'll declare an I for I equal to 0, I less than 10. We can fill it up. I plus plus, or I is equal to I plus 1. Now we'll say p ARR of I is equal to I plus 1. Okay. Then we'll say p is equal to ARR and star of p is equal to 10. Then printf ARR of 0 percentage d. Okay. Yeah, you get the answer as 10. Now, why did you get 10? Yeah, go back. He's gone to sleep or what? Sharan?
We can write P equal to ampersand.
Go back. Huh? We can write P is equal to ampersand.
So that comment, Chapman.
Star P. We can say P is equal to.
Ampersand.
No, go to the comment. We can write P is equal to address of ADD 0. Yeah, you can do that. ADD
of
10.
a particular element.
We can always write it as an address of a particular element, no problem. If that is what you are trying to say there. Okay. Okay. So, yeah. So we have now some correspondence between arrays. See, this line is very important. This line. P is equal to AR, where we have said AR is the name of the array. We also said the name of the array is itself the address of the first element. So now P is pointing to the first element. When we say star of P is equal to 10, the first element, which is ARR0, changes and it becomes 10. So that is what we have effectively done. Okay. So if you are clear up to this point, we have made good progress and we can move on. So now, okay, let's play with this example a little bit. Okay. Okay, I'm going to take a small leap ahead to illustrate a more important concept or a related concept. Now, let's say I have ARR. Okay. And as you can see, the values are from 1 to 10. 1 all the way up to 10 because I said I plus 1. Right? Now, I have made P hold this address of this address. So let's say this is at 1000. Let's say the array is at 1000. Okay. Okay. So P holds the number or P holds the address of the array, address of the first element. When you say P is equal to ARR, P will hold the address of the first element, which is 1000. Okay. Now, when I say star of P is equal to 10, this value changed from 1 to 10. Okay. Now, we are playing with this a little more. Suppose I say now P, okay, is equal to P plus 1. Then I say star of P is equal to 11. What do you think this will do? Please remember, P is a pointer. P is not a number. P is a pointer. And on pointer, I am adding a number. I am adding 1. So, this is not a regular number arithmetic. This is pointer arithmetic. I am doing some arithmetic on pointers. So, I am saying P is equal to P plus 1. Then I am saying star of P is equal to 11. Okay. What will this do? What will be the effect of this line? P is equal to P plus 1. Right now, P is at name of the array. You see this code. So let's say after this line, I put these two lines. Okay. I put these two lines after this line. This is first, this is next. And after that, I print, or I am just asking, what is the impact of this line? Okay. Now this will get erased, right?
No, sir.
This will, no, when we go to chat, let it be. Okay. So what will happen? Somebody is getting it right. So ARR1 Yeah, very good. ARR 1 will become 11. Very good. ARR of 1 will become 11. Yeah. Now let's go back and understand why that happens. So now what's going to happen is, when I say star of P is equal to 11, okay, where is P pointing now? P is equal to P plus 1. When I do pointer arithmetic on pointers, it finds out what is P pointing to. It is pointing to 1000. And what is the kind of pointer it is? Integer pointer. Remember, P is an integer pointer. So when I do P plus 1, it doesn't become 1001, it becomes 1004. It becomes 1004. Now you'll ask, why did it become 1004? Because P is an integer pointer. Whenever I increment the integer pointer, it will point to the next integer. If it has to point to the next integer, what should its address be? Should it not be 1004? Because pointer, the size of an integer itself is 4 bytes. So before this line, P was at pointing to the first location of the array. Now P will point to the next location of the array. Why? Because P plus 1 means it will point to the next integer. It will increment by 1. Pointer will increment by 1 means the address will increment by 4. Okay. So if you want, we can even check it and print it in decimal positions. Let's do this so that you get a better picture. Okay. Let's.
Someone has interesting questions.
Huh?
Someone has some interesting question.
Interesting question. Okay. Let's see interesting question somewhere, right?
Yeah, that question.
Why are we using pointers? How will we use them in future? Yeah, you will soon learn. Yeah. Why are we using pointers? Okay. So, okay, okay, let's do this once and see. Okay. So we say P is equal to P plus 1. Okay. No, okay, before that, let's print the pointer. No, print percentage D P is equal to pattern. Next line now.
This one.
P is equal to, I am printing the pointer in decimal notation. Generally we don't do it that way, but just to address of P call.
No value of P.
P, P is, then
Star.
just print P.
Just
Then
print
say P is equal to P plus 1.
So
Then tarvata again print P.
just print P will give the address of variable. Right? Just print P will give the address of variable. Right?
It will give whatever is the content, no? P is the address of ARR, no?
Yes, sir.
So it will give you the address of ARR. Now it will give you the next address. Only thing we should see is, we should see P incremented by 4.
Oh.
Okay. So let's see this. P should get incremented by 4 because, don't worry so much about the, it may be incremented by 4 or decremented by 4. Don't bother.
Every time increment on this.
No, it can go lesser in memory or more in memory. If it is a negative address,
Negative.
even then it's an increment only.
Yeah.
So if you notice this, you see this is 72. This is 72 minus, and this is minus 68. So just imagine minus 72 is somewhere here. Okay. Minus 68 will be here. I'm just looking at the last value. Forget why you are getting a negative number. Okay. That's why we print hexadecimal. Okay. This is minus 72. This is minus 68. You see there? we are getting, so this difference between these two locations is 4 bytes. You see there, 72, 68. Rest of it is same. So an address which is minus 72 is now become minus 68. That means pointer has moved ahead. If you want further, if I again increment p, I'll get here 64. Okay? Or if you increment p by 2, you'll get it as 64. You can do that. These are all addresses. Don't worry why they are negative. They're just numbers. Okay, let's do p plus 2 and check. P plus 2. नहीं अकड़े चेयंडी अकड़े instead of p plus 1 p plus 2 పెట్టండి. Yeah. Now a completely different address, does not matter, but if you see you'll understand what happened. Okay. No, sorry. The first address was at minus 24. Now because it was p plus 2, the next address would have been minus 20. The address after that is minus 60. See this, 60. Rest of it is same. Okay. So it moved ahead by 1 plus 1. So this is p plus 1 and this is p plus 2. This one. Right? So that's how it moves. Because it is moving by 4 bytes. Because in our systems, integer is a 4 bytes long. So when you go to the next address, it moves by 4. Okay. The next address of the next integer will be 4 bytes away. Okay. So now let's go back. Okay. Now somebody asked me a question. Why do I have pointers? Okay. Now I don't know whether it's too premature to say this. I'll say it nevertheless. In C, at the core of the language, that is at the lowest level or the innermost level of the language, there is no arrays. There are no arrays, or there is no array. There is no array. No array. An array is a pointer. Meaning, what they have in the language, at the core of the language, is only pointers. And the concept of an array, though it looks to us like an array, internally it's an idea of a pointer only. So they have actually given us the benefit of this array, but actually what they are dealing with internally is pointers only. The language at the lowest level, at its innermost level, language C, has no concept of an array. Concept of an array is created for our benefit, for enabling us to work easily. But whatever the C compiler does, whenever it sees this, it is converting this into a pointer only. Okay. So that is very important to understand. So far whenever we have been dealing with arrays, so far whenever we have been dealing with arrays, whenever we have said int ARR 0, int ARR 10, and then we have said ARR of 5, let's say, equal to 7, what the C compiler has actually done is star of ARR plus 5. Is it plus 5? Yeah. ARR plus 5 is equal to 7. When it says you are doing this, internally array is what? Pointer to the first element. So internally what it is doing, when you say ARR of 5, this is getting translated to this. Because I told you ARR is a pointer to the first element. The name of the array is a pointer to the first element. So when you say ARR 5, the compiler looks at it and converts it into this. Okay. And when you say printf percentage of D ARR I, when you say like this, okay, what it is doing? It is saying printf percentage D, it is saying star of ARR plus I. That's all it is doing. When you are saying ARR of I, it is saying ARR plus I star of that. That is, this is a pointer. Add I value to it. Move the pointer forward. Say star of ARR of 5. So internally in C, everything is a pointer. There is no array. So the idea of an array itself is implemented through the idea of a pointer. So that's very important to understand. Now this will take a little while to get in, but once you get this in, you will not use this notation. There are a lot of people, lot of professional C programmers, they don't ever say ARR of I. They say star of ARR plus I. Okay. They don't use this notation at all. They use only this notation. A lot of very proficient C programmers, they will use this notation. They don't use this because they know anyway the compiler is going to convert this into this. So why don't I write it like this only? So that is the advantage or that is the benefit. Now let us play with this little more and let's write this. For those of you a little slow, yeah. So let me elaborate on that. Let's work with the same example. No, remove from 10 on. No, we will remove from 10 onwards. We'll write it again, whatever we write. Okay. Now just see this. Okay. Now I will print the array using a loop. But look at the way I am writing the loop. For I equal to 0, I less than 10, I equal to I plus 1 remains the same. Open the loop. Okay. I'll say printf. I'll print it in that notation. Printf. Okay. Percentage D. Okay. No, you have to give a space so that values stand out. Percentage D.
You give char space or one space?
No, just space. Space star of ARR star bracket ARR plus I. ARR, Baba.
Yes, I get.
See this now. You will get the array printed. See that. I didn't print the array using ARR of I notation. Go back. Now let's see what happened. Okay. So, yeah. So why did this work? What is ARR? Name of the array. Name of the array is what? Address of the address or pointer. It's a constant pointer, it can't change. Address or pointer to the first element. So here ARR is a pointer to the first element. So imagine this is your ARR. So ARR first is here. So ARR will always be here by the way. So ARR plus I is what? Is this value, because first time I is 0, it prints whatever is there here, the value 0, right? The index, whatever is the value at index 0. Then in the next iteration, I is 1. So what is ARR plus 1? ARR plus 1 is the address of this. ARR is the address of the first element. ARR plus 1 will be what? Address of the second element. Star of that, what it will do? The value at that element. So it will print that. Then ARR plus 2, this is ARR. This is the address of this location is ARR. The address of this location is ARR plus 1. The address of this location is ARR plus 2, and so on. The address of this location is ARR plus 9, right? Or this can be called ARR plus 0. So this is ARR plus 0, ARR plus 1, ARR plus 2. I am going to each of those locations. I am doing dereferencing. So if you see, I am doing dereferencing. Okay. Now I can change this also. I don't need this way of assignment also. I can, instead of this, I can use the referencing and assign the value. So can I change this? Yes, I can change this also. So let's see how I can change that. What should you write there? So what will I write there? Star of ARR plus I, star of ARR plus I is equal to I plus 1. That's all. So ARR plus Y is the pointer. Star of I gets the dereferencing of the pointer, and go to that location, put this value. So so let's change that. In place of ARR of I, we'll say star of ARR plus I. Star of ARR plus I. So that is nothing but the same thing, which is equivalent. Okay. So let's run it. So I get those values. Okay, again, no change. Okay. So I think we have covered quite a bit today. I don't want to go much more forward because this will need a little bit of revisiting and thing. Now, is some of it making sense?
Few questions.
Yeah, for the pointer to work, we have to declare an array.
I don't know, sir.
Yeah, you have to create, storage has to be given using the array as of now. Later we can take the storage using an malloc. Okay. If we take P is equal to ARR, then start of P plus I will print the array. Yes, it will print the array. Why not? Can you please give us practice? No, we'll do. I am asking, they are not yet ready. So we'll create a practice examples and give you a whole lot, because now we have made progress. If we are, sir, if you are able to do P is equal to P is equal to ARR and star P plus I will print all the array. Yes. Yeah, I think that was the question. Okay. Yeah, it will print. If you want, we can do it. Why address is different for every run? Well, that is arbitrarily assigned by the compiler. There is never a fixed address. Every time you compile, you will get a different address because the program will sit in a different area of memory. It will not stay in the same area of memory when the program runs. It is controlled by the operating system. So whatever address operating system assigns to the program will be given. Okay, and that will change every time. how we allocate array using pointers? Yes, we'll come to that. Not yet. Okay. No. Mid-exam and all, I am exam indifferent. I don't talk about exams. Okay. Because I think exams are a waste of time. You just learn. For me, that is more important. Okay, so I don't keep track. When is your exam? What is the syllabus? What is all that? Has no value. Okay. Yeah, but the right people will get back to you with the message. Okay. So I think, did we record? No.
Yeah, we are recording. We are recording and we are uploading in the.
Achha, they are recording and uploading, I think. Okay. But you are not uploading to
Vista.
Vista.
Yes.
Achha, it's getting recorded. No, you should, Baba. You should ensure that it get.
But we are sharing in the KMITonline.com.
You do it in KMIT online also. Share it on Vista also,
Okay, sure.
because everything is coming to Vista. No.
Oh.
Okay. So you can go through this class again. No, I think we have to put this class up fast so that they can revise pointers. Okay. So this was our introductory lecture on pointers. We covered quite a bit of ground. It is good. Now I am not going to cover too much today. I am going to stop here and we will work with pointers some more all through. In fact, now that you know pointers, most of the C will be a piece of cake. Most of the remaining C will be just a piece of cake. Okay. Where do you place the video? Okay, we'll just show you. We place it under, see, earlier videos when we were live, I mean live in the sense we were offline, they are all on KMIT Vista. That I think you know. Now the things which are not there are here. Okay?
Under study material.
They are under KMIT study material. If you open up KMIT study material from your login page, from the dashboard, you will see there are many things there, so you need to go to the right place.